Hey guys, this week so far y'all have checked out, um, I believe on Tuesday, this reading on the exponential function in your binder. Kind of looked at the exponential function, how it's built up and created, where b is now your rate, and a is your starting point, and an exponential function, kind of like your y equals mx plus b, just now b is your slope and a is your y-intercept. And you kind of read through here and checked out some of the transformations of this function. On Wednesday, you had an activity, an assignment similar to this that I posted right here on Canvas, and you played around with it. And then I even put the answer sheet on there so you can see how the transformations of a natural exponential function kind of behave. Well, you have your generic y equals ab to the x equation, but what if I add a number to the x, like in this scenario? What happens? Well, like in every other scenario, when you add a number or subtract a number to the x, it moves the graph to the left or to the right. Just like all the other functions we've done with quadratics and cubics and cube roots. What if we added or subtracted a number to the entire function on the outside of the x? Well, that's what happens here with the plus or minus k, where it shifts the graph like all the other ones. It shifts it up or it shifts it downwards. All you got to do, though, is remember that with the a value here inside, x's lie. So if it says plus, then it's going left. If it says minus, it's going right. And then we also checked out some of the transformations. What if we made the x value negative? Or what if we made the x value, or the value in front of the e negative? It kind of flips the graph. Now that we've looked at the function, and we've looked at the exponential and how it moves around a graph, you've dealt with that in Algebra 1, so the college moves on pretty quickly after that. Because you've seen exponentials, you've seen growth and decay of a graph, and we even talked about in last week's discussion. So now they jump straight into what's called a logarithm right after this. And right here is where you kind of get a reason why they jump into logarithms. It says in this first sentence, the logarithmic function is the inverse of the exponential function. Well, inverse once again means a flipping of the roles of the x and the y's. Or as the college says, that is, the logarithmic function switches the domain and range, the x and the y's, of the exponential function. So however the exponential behaves, the logarithm kind of flips that stuff around on its head. Now, I'm only going to focus on this part for today and the next day, because the rest of this is going to be for exercise later on. So we're going to focus on this top part. If I scroll down here, we're also going to focus on this little chart as well. Because within this chart, you can now do the next exercise, these 7 through 10 problems. And then this reading that we're skipping here is going to be the exercise after that, which is 10.2.4, more logarithm practice. So that's why we're going to skip it for now. So if you remember in exponential functions and what you did on last week Friday and this week Monday, you did exponent rules. You did exponent rules to where with the Euler's number, where if you had e to the second and it's multiplying to another Euler's number, e to the third, well, to combine those two e's into one e, what did you do with the 2 and the 3? Well, since it was multiplying, you added the exponents and found out that this is e to the fifth. Similar with, we did the same thing, e to the third, but then with division, e to the second. If we want to combine these two e's into one singular e, since it was dividing, we subtracted the two exponents and found out that this condenses down to one singular e of e to the first. Those are rules that y'all should have a pretty good handle on. But now logarithms are the inverse function. If you want to combine two logs together, we're going to do something that's similar to what we just did with exponent rules, but it's going to flip something on its head. Watch this. We have, for example, log of, let's use the same numbers, 2, but we're going to add in this case, log of 3. This is where it flips the rules on its head a little bit. Instead of saying when I see multiplication, I add the exponents. With logs, when you see addition of two logs, to combine it to a singular log, you multiply the numbers inside the parentheses. And so now we get a singular log of log 6. See how that kind of worked out? The inverse from exponential to log is if you see addition, you multiply. So then if we try this example with subtraction now, log 2 minus log 3. Similar example. When we see subtraction in logs, if we want to condense it down to a singular log, we divide. Notice how I took the 2 and it was the number on top. I took the 3, it was the number on bottom. This being because the 3 had a negative sign in front of it. It was a minus log. So that 3 gets to go on bottom, while the positive log, since it's a positive, goes on top. And so now we've condensed that down to a singular log. So in exponents, when you multiply, you add the exponents. In logs, when you add, you multiply the numbers inside. That's where the inverse comes into play. So if we check out the box, they give us a property, an example, and ask us for a solution. They give us the property when two logs are adding. You multiply the m and the n, the inside parentheses. In the example, they've already combined something together. Our thing is to figure out what were the options they could have combined. Well, to get log base 5 of 12, they could have done several things. They could have done log base 5 of 2 plus log base 5 of 6. And then when I multiply 6 and 2, I would get 12. Now, they could have also done something else too, right? They could have done something different to be able to get 12 instead of just doing 6 and 2. What other numbers could they have done? They could have done 1 and 12. 1 times 12 is 12. They could have done 3 and 4. Can you think of another way? 1, 12, 2, 6, 3, 4. There is one more way they could have done. That's kind of challenging for you to think about. They could have used a third log. They could have combined 3 logs together to make the number 12 when multiplied. What could they have done? Well, we know they could have done 2 times 2 times 3, because 2 times 2 times 3 is 12. They could have also done 1 times 1 times 12. But looking at this scenario, you probably could understand that they could do an infinite amount of logs, because I can keep having log 5, 1, log 5, 1, log 5, 1 infinitely, plus log 12. So those are all the different scenarios they could have done, but for our notes, I'm just going to leave it simple. Let's just put a simple example up here. Let's put up here, and this will be the only one I go this far on. Log 5, 3 plus log 5. Oh, sorry, put it in the wrong spot. Let me delete that. Log 5, 4. So for your notes, simple example. The next one, what could they have done here? Well, they probably could have done log x, but notice there's a division happening. With the division, we'll put the 5 in this parenthesis, since it's on top, and we'll minus off the log x of 2. And so we get 5 halves, because since the 2 logs are minusing, we divide to combine into 1 log. Now, you may be thinking this is the only way this problem could have turned out. But there are other ways. Can you think of any other ways that you could have gotten 5 halves from in the division? Think about it. There's an infinite amount of answers here too, because I could have gotten 5 halves if I did log x 10 minus log x 4. 10 over 4 reduces to 5 halves. Log x 15 minus log x 6, because 15 over 6 reduces. So there's an infinite amount of answers there as also, but just wanted to check that out. Alright. Those two were pretty straightforward because you've seen those in exponential laws there. This other one is a simple rule, but it's new to you. Notice how in this rule here, we have a simple log base b m to the k power. Notice what they did in the equation to the right. They took the exponent k and they dropped it in front of the log. Now we were supposed to look at proofs on why you could do this in class, but we will skip this. For now, let's just understand that that is a logical way of doing logarithms, of simplifying. So for example, if you look at this example, what could the solution be? Well, it could be log a 7 squared, couldn't it? Because the 2 can simply just go up and be an exponent based on the rule they gave us. Can you see something else I could do? Could also be log, what is that, base A? Base A, 49. Where they probably had 49, then they extracted the square from it, and then they put the 2 in front. So this can go either way here. And last one is called the change of base formula. This one was important back before calculators had a log button for you to be able to calculate it, because in the past you couldn't put a base number into a calculator. But nowadays you can simply just plug in log 2, 4 and pop out an answer. But with the change of base formula, it's important when used in proofs, and so I'll show it here. All a change of base formula is, if you can't input the 2 into a calculator and calculate it, you could do a change of base formula, which is log 4 divided by log 2, and it pops out the same answer. It's just a way to write the answer in a calculator so that it can calculate it if you can't put the base number of 2 in a normal 4 function calculator. Hence, as if you're taking the SAT test or ACT and they don't allow that. So there's the rules. Let's scoot down to the activity down here. I believe I assigned y'all 7 through 12. We'll do a few of these together real quick, just to make sure we got it together. Let's look at number 7. If we were to number these rules that we did in the box, we'll number 1, 2, 3, 4. And so number 7 is using which rule in the box? It's using number 3. Because if you notice, they just want you to write this as a single logarithm. Well, it's already a single logarithm. So what else can you do? Oh, I can move the 4 up to condense the log down just a little bit. And so it could be read as log base 23 to the 4th power. Now I could also write this out even further, log base 2 of 281, because that's 3 to the 4th is 281. And so I could have simplified it more, but we'll leave it like that for now. Let's check out number 9. Now look here, we're trying to condense these down to one log. Notice there are 3 logs. So I know my result is going to come out to be a singular log, log 2, because they're all log 2s. That's the only way you can combine logs, if it's the same logarithm. And so if I look at this, I have a positive log, a positive log. Those will go on top. 225. Oh, let me get out of this little area here. Let's put the answer down here instead. Log 2. We'll put 225 and times 3. Since they're both positive logs, they're multiplying on top. And since this one's a negative log, you'll be dividing on bottom. Now I could simplify that out a little bit more, but that's the gist of the answer. I can keep going and do the division of these two numbers, because we learned in rational functions units that you can, if these are factors, you can divide these things out individually. So 225 divided by 5 is going to give me 45. And then I still have 45 times 3, which will give me 135. So technically, this is a better answer to write. Alright, let's check out another problem. Alright, let's look at, we'll look at this one, number 12. We've got here, we're going to combine these logs into a single argument. Log 5 as one argument. But you see here, before we combine these, step that is easier. Yes, I notice this is a positive log, that is a negative log. I know that there's going to be a division. What would be easier is if I move this 3 up first. I move it up as an exponent. So now it's a little bit simpler. And then I can combine the two arguments. This is 54 since it's a positive log on top. And since this is a negative log, I'll put 3 to the third on bottom. Or 3 to the third is 27. So this value is 27. And then I can simplify it a little bit more and get to log 5 of 2. There's number 12. I think that pretty much covers all the different examples and illustrations I can. All the other ones are iteration from what we just did. A natural log is going to follow the same rules as a regular log. ln, by the way, that's a L and an N. And it stands for natural log. You should have approached this in your reading before, that natural log. The reason that we have this is because a natural log's base, when you don't see a base, is assumed to be the base of e. So this is actually what number 11 is written out if I don't imply the base number, if I actually write it. Now a log, when you don't have a base number, the implication is that it's the number 10, like 10 is what we count by. But 11 will follow the same properties.